Hello and welcome to week 2 of ELEC50B. Let me share my screen real quick. All right, so last week we ended up where we ended up talking about the sine wave and calculating the instantaneous value. So this week we're going to continue our conversation and look at some of the terms that we need to know for these AC signals. First one is the frequency and the period. Now, the frequency and the period are inverses of each other. So the frequency is 1 over the period, and the period is 1 over the frequency. And remember that in the United States, we're on a 60 hertz system, whereas in Europe, they're on a 50 hertz system, which means 60 cycles per second or 50 cycles per second. Right? And then here's a list of some of the various things, like, for example, wireless communication is usually in the 2.4 gigahertz band or the 5 gigahertz band, with Wi-Fi 7 being in Wi-Fi 6 in the 6 gigahertz band as well. All right. So the period is the amount of time it takes a waveform to complete one cycle, and T is the symbol for that. So a 60 hertz waveform has the inverse of 1 over 60. So if we look at our camera here, let me switch camera, stop share, and go to my calculator here. So if our frequency is 60, our time period will be 1 over that. So 1 divided by 60 is going to be 16.667 milliseconds, right? So that's how we would calculate that. And then the opposite would be true if we said, what is the period of 100 megahertz signal? So if we go 100 mega would be to the millionth, right? So that's 6. And then take 1 over that. So we can take the inverse of that, which is, I can't, my screen's kind of sideways here, but 1 divided by 100 exponent 6 is 10 to the negative 9 seconds, which is what, nanoseconds, right? So it's really easy to work with those values. All right, so let me switch back to my camera and then go back to my screen. All right, so that's the frequency and the period. Those are really easy to calculate. So determine the frequency of 3,500 kilohertz. You just take the period would be 1 over 35 times 10 to the third. Was the frequency of a waveform whose period is 120 microseconds, so it'll be 120 EE 10 to the negative 6. And you can calculate those. Those are fairly easy. Now, there's other waveforms that aren't always a sine wave, square waves, triangle waves, sawtooth waves. And you'll experience that in lab, where you use a function generator to create different things there. Now, the wavelength, the term wavelength here is referring to how long is that wave, right? So the distance is simply the velocity times the time. The distance equals velocity of time. Since frequency is reciprocal of time, the distance for a line may be rewritten as the distance equals the velocity divided by the frequency, which is just 1 over time is 1 over the frequency. So that's where you get that value from. And then the wavelength is given in the Greek symbol lambda, where the lambda equals the velocity divided by the frequency. So you can see where these are here. But in time, is the period, and then the wavelength is the distance that it takes in that amount of time. All right, so you can calculate that. And remember, speed of light is 3 × 10⁸ meters per second. So there's some calculations here that you can go back and look at. All right. And another concept that we want to be aware of is the phase relationship. So the phase relationship is referring to where one signal is either in front of or behind or leading or lagging the other wave. So in this case, these two are in phase. This one, this one is leading the blue one, the red one's leading the blue one by 90 degrees. And here they're 180 degrees out of phase. And then in this one, the red is leading the blue by 90 degrees. Okay. So you can see where, how these are doing that. So in the first wave, because they cross, they're in phase. In the second, the red curve is leading the blue by 90, or the blue one is lagging the red by 90. In the third one, the figures are 180 degrees out of phase. And then in the fourth one, the blue curve crosses the reference line in the positive direction after the red one, or 90 degrees before the red one. Okay. So in other words, the blue's leading the red, or the red's lagging the blue. All right. And we're going to see this with various signals. Now, the relationship between cosine and sine is that the phase angles are 90 degrees different. So the cosine wave is lagging the sine wave by 90 degrees. Okay, so it's just straightforward stuff. You can refer to this chapter and really get a good idea for this. Now, when we're looking at our oscilloscope, we want to make sure that they're on the same time frame, same time frequency. So here is where we have 3 signals, right? V1, V2, and V3. And if we show those in a phasor diagram, it looks like this. So the phasor diagram, this is time base, and then this is the phasor diagram. All right. And we can see here that V1 lags V2 by 45 degrees, and then V1 leads V3 by 45 degrees. And then V2 leads V1 by 45 degrees, and V2 leads V3 by 90 degrees. And then V3 lags V1 by 45 and V2 by 90. You can look at this phasor diagram to see all of that information as well. All right. Now, there's other non-sinusoidal waveforms that we can look at. So like the square wave, television, music, digital, and so forth, all produce non-sinusoidal waveforms. And with these non-sinusoidal, they do not have to be in perfect sequence where the on time and the off time are equal. So for example, here we have the on time is this width, and the off time is down here. So it's positive or on right here, and then it's off right there. So the way we can calculate that is we can measure the rise time and the fall time as a percentage. And the calculation for that is the DC or duty cycle is equal to the pulse width divided by the time. So for example, if we have a duty cycle when the pulse width, determine the duty cycle when the pulse width is 200 microseconds and the period is 1000 microseconds. So if you take 200 divided by 1,000, you get 0.2, which is a 20% duty cycle, which means it's on 20% of the time and then off the 80% of the time. Now, a higher duty cycle means that the load receives more average voltage and therefore is on longer. DC motor speed is controlled this way using pulse width modulation. And the average value of the pulse wave is found by multiplying the duty cycle by the peak to peak voltage. So we can see this where the average time is the baseline plus the duty cycle times the VPP. So we can calculate that. All right. So if we were to determine the average value of the pulse width waveform shown below, so it's on for 400 microseconds at 7 volts, and it's off for 1600 microseconds at -3 volts. Calculations would be the time equals the pulse width times plus the time pulse is low, which would be 2000 microseconds. And then we would take 400 divided by 2000 is 0.2. And then it's 7 volts minus 3 volts is 10 volts. And then multiply that, -3 volts plus 0.2 times 10 volts, it comes out at a -1 volt. Okay, so that's the calculations that you would do. And you'll need to calculate that for homework too. All right, so determine the average value of the pulse waveform shown below. This is going to be the calculations would be there. And this is at the end of the chapter where it shows you how to do those calculations. All right. And then the rest of the chapter just has a little bit more to do with the duty cycle, non-sinusoidal, square wave, triangle, and so forth. And there's a discussion on here about harmonics, which will come later in the course where we'll work more with harmonics, where you can see those are signals kind of encapsulated in other signals and so forth. And that's it for chapter 14. All right, so let me bring up chapter 15 and we'll talk about some test equipment. All right, so let me get back in here and share my screen again. And then we'll talk about the test equipment. And this is stuff that you're going to do in this week's lab. Okay, you did a little bit in last week's lab and you also do it here. So the topics here are listed, and let me see here. Let's stop the video.